you've heard me mention compilers. A compiler is a software tool that translates code written in a high-level programming language, like C, C++, and Python, into a lower-level language such as machine code, assembly, or intermediate bytecode. Now, although I mentioned Python, it's not traditionally compiled in the same way as languages like C and C++. Instead, Python is primarily an interpreted language with a mix of compilation steps that happen behind the scenes. I'll loop back to this to discuss how it's applicable when we're talking about compilers. The code translation compilers perform enables programs to execute on a computer or other hardware. Compilers work with lexical analysis, breaking the source code into tokens, like keywords and identifiers, with syntax analysis, checking the structure of the code against grammar rules, with semantic analysis, ensuring logical consistency and checks for type mismatches, with intermediate code generation, converting the code into an intermediate representation, IR, with optimization, enhancing performance by removing redundant instructions or optimizing resource usage, with code generation, producing machine code or bytecode for execution, and with linking, combining machine code with libraries and dependencies into an executable. In the 1940s and 1950s, early computers were programmed in machine code, where every instruction had to be entered manually. Assembler tools were created to translate symbolic assembly language into machine code. In 1952, the first modern compiler, written by Grace Hopper, was developed for the A through 0 system. Hopper's compiler demonstrated that machines could translate high-level instructions into machine-readable code. In 1957, the Fortran compiler, created by IBM, became one of the first widely used high-level language compilers. In the 1960s through the 1980s, the development of C and C++ led to more sophisticated compilers. The rise of cross-platform compilers allowed code to run on multiple architectures. In the 1990s to the 2000s, the evolution of just-in-time JIT compilers for languages like Java and .NET introduced dynamic code generation at runtime. Compilers became integrated with integrated development environments. In present days, compilers like GCC, CLang and LLVM, and MSVC support advanced features such as static analysis, security hardening, and performance optimizations. Compilers play their role in cybersecurity. They enable secure coding practices. Compilers can enforce strong type checking, memory safety, and logical consistency during code compilation. For example, they prevent buffer overflows by identifying unsafe operations in languages like C. They only prevent some buffer overflows, though. They also help to generate secure executables. Compilers embed security mechanisms into the binary code. There's stack canaries, which protect against stack buffer overflows. There's address space layout randomization, ASLR, introduced via linker flags to randomize memory layout. And there is control flow integrity, ensuring control flow adheres to intended execution paths. Compilers are instrumental in mitigating vulnerabilities like Spectre and Meltdown. There are the retpo lines that are added to binaries during compilation to block speculative execution attacks, and memory barriers like LFENTs are inserted to prevent speculative vulnerabilities. Modern compilers integrate static analysis tools to detect potential vulnerabilities such as the use of uninitialized variables, buffer overflows, and null pointer dereferences. Examples of compiler flags that improve security is the fstack protector, which adds stack canaries to protect against stack-based attacks. The dfortify source equals 2, which strengthens string handling functions, and the fpi and fpick, which generate position-independent code to support ASLR. Compilers can produce obfuscated code, making it harder for attackers to reverse engineer binaries. For example, stripping debugging symbols to hide internal logic. Compilers are used in a dual role, really, for malware creation and detection. As attackers use compilers to build malicious code, security teams use compilers and decompilers for malware analyses, reverse engineering, and signature creation. Compilers have a positive impact on cybersecurity with automated security. Compilers enforce rules that prevent common programming errors and optimize security mitigations. Compilers produce hardened code to resist exploitation, and static analyses, detecting vulnerabilities before deployment. Compilers also have a negative impact on cybersecurity. Attackers can use compilers to create platform-specific exploits, and custom compilers enable malware obfuscation or polymorphism, making detection harder. Challenges associated with compilers: there can be a false sense of security. Developers might rely too heavily on compiler protections and overlook some important secure coding practices. There may be performance trade-offs. Security measures such as stat canaries or ASLR may introduce runtime overhead. Legacy systems: older compilers lack modern security features, leaving legacy systems vulnerable. Compilers are foundational to modern software development and play a dual role in cybersecurity. They help developers build secure applications while also being exploited by attackers to create malicious code. The evolution of compilers, from basic translators to tools capable of enforcing advanced security measures, demonstrates their critical importance in this ongoing battle to protect digital systems.